Welcome to my classroom. In this video, I use some simple examples to give a brief idea of cryptography, including symmetric encryption, asymmetric decryption, digital signature, blockchain, and Bitcoin. A book on cryptography and a video on Bitcoin I'll recommend at the end of the video. Cryptography has a long history. In ancient times, people used simple but useful methods to convert messages so that the encrypted messages could not be understood by the enemies in war. The methods used at that time are symmetric. That means the same key is used for encryption and decryption. Here, I use an example of Caesar cipher to show the idea. Suppose the plain text is hello. The encryption key is a right shift of 3. Then H is shift to K, E to H, L to O, and O to R. That is, the ciphertext is. It is not easy for others to associate hello from this text, right? This is the purpose of cryptography. To decrypt the ciphertext, just reverse the directions. That is, the decryption key is a left shift of 3. In other words, from this we get hello back. There are many variations of setting the encryption key. You may try and think of other creative choices of the key for the encryption. Symmetric encryption is simple and easy. There is only one key, which is shared between senders and receivers. It is easy to be hacked by others. Later on, for sensitive data, more often, asymmetric encryption is used. The example I use here is RSA Cipher. It was created in 1977 by 3 mathematicians. RSA refers to the first letters of their surnames. The core idea of this cipher is based on a one-way function and the Euler's theorem discussed in my last video. Here, I recall the idea and work with an example. Suppose P and Q are 2 large primes. Let n equals P times Q. Then the number of positive integers less than n is given by phi n. That is, P minus 1 times Q minus 1. Take a positive integer h, which is less than phi n, where h and phi n are relatively prime. We got the public keys as n and h, and the private key as p and q. Given a plain text p, and denote the ciphertext by c. Encryption is done by using the power function with the public keys, that is, c congruent to p to the power h mod n. For decryption, first solve the equation hx congruent to 1 mod phi n by using Euclidean division. Suppose the solution is k, that is, h times k congruent to 1 mod phi n. Then, by Euler's theorem, we have p congruent to c to the power k mod n. I don't know if you have watched my last video and have done the exercise for checking the inverse function. Here is the verification. Since k is the solution, that is, then c to the power k is congruent to p mod n. The congruent sign is guaranteed by Euler's theorem. For a better demonstration, the following simple examples shows the working. I use 2 small primes, p equals 7, q equals 13 for easy calculation. Then n is 91, and phi n is 72. Take h equals 11, which is less than and relatively prime to 72. Suppose the plain text is 25. For encryption, that is, change plain text to ciphertext. C is congruent to 51 mod 191. For decryption, that is, turn ciphertext back to plain text. First, Solve the equation 11x congruence to 1 mod 72. I solved this equation in the last video with Euclidean division, and the solution is x congruence to 59 mod 72. Then the plain text is p congruence to 25 mod 191. Note that the decryption is the reverse process of encryption. Thus, 25 goes to 51 by encryption, and 51 goes back to 25 by decryption. Asymmetric encryption requires two keys, public key and private key for encryption and decryption, and it involves the use of a one-way function. That is, if only the public key is given, we have no idea of getting the private key, as it is hard to find the inverse of the one-way function. Here, I use a one-way function to show how two persons share a key without key distribution. To make calculation easy, the one-way function used here is a simple one. Suppose David and Sarah agree on the one-way function fx congruence to 7 to the power x mod 11. It is easy to calculate the function value, say f of a by substitution, but hard to reverse the calculation, that is, to solve the equation like fx equals to a. Okay, David and Sarah each chooses a number and keeps it on their own secretly. Suppose David chooses 3 and label it as a, and Sarah chooses 6 and label it as b. David puts 3 into the one-way function and gets 2. Let the result be alpha. Sarah puts 6 into the function and gets 4. Let the result be beta. They send their results to each other. That is, David sends alpha to Sarah and Sarah sends beta to David. David uses the results from Sarah as the base and his chosen number as the power and finds 9. Similarly, Sarah takes 2 to the power 6 mod 11 and gets 9 as well, due to the fact that they get the key 9 without meeting or sending their keys to each other. That is, there is no key distribution. In this process, 7 and 11 are public keys. The numbers can be disclosed to others. 3 and 6 are private keys. They are kept secretly by the users. When I taught the chapter of exponential functions in my class, I usually started with a story of putting games on a checkbox of 64 squares to help my students imagine the power of the exponential function y equals to 2 to the power x. It increases slowly at the beginning, 2, 4, 8, 16, small numbers in the beginning. But when it takes more terms, say 64, how big is 2 to the power 64? Check with calculators. It is 1.8 times 10 to the power 19. The world population in 2022 is 7.9 billion, that is 7.9 times 10 to the power 9. 2 to the power 64 is more than the world population by 2.3 times 10 to the power 9 times. 2 to the power 64 is a huge number that makes a king go bankrupt. Think about 2 to the power 256. What do you feel? This number is greater than 1.1 times 10 to the power 77. This big number is good for cryptography. Now, an algorithm is called SHA 256, where SHA stands for Secure Hash Algorithm. It works like a one-way function, and the output contains 256 digits of 0 or 1. That means there are 2 to the power 256 possible outcomes. The extremely large number of choices is used for digital signature. Digital signature is a method to confirm the validity of messages transferred in Internet. A message is first converted by the function SHA 256 into a string of 256 digits of 0 and 1. as 2 to the power 256 is a huge number, a slight difference of the message gives a completely different string of 0 and 1. Let me use a simple example to illustrate this idea. Suppose David has posted a message, the original data, in the internet. Sarah reads the message, received data from the internet. How can Sarah confirm the message received is true? That is, no hackers change the content, and the message is sent by David? The way to solve this is to use digital signature. David adds his digital signature on the original data and sends the results together with his public key to Sarah for verification. Here is the process of adding digital signature and the verification. David applies the function SHA-256 on his original data, and the result is denoted by A. He then encrypts A by his private key and gets B. Then B is the digital signature on the message. He sends B with his public key to Sarah. Sarah decrypts B by David's public key and gets C. Sarah applies the function SHA-256 on the received data from the internet and gets D. If C equals D, then Sarah can confirm the received data is same as the original data. That is, the message is true, and it is posted by David. In this way, using the function SHA-256, digital signature is done to guarantee both the message and the sender are genuine. With the techniques of securing the sensitive data by various encryption and digital signature, the idea of decentralized currency Bitcoin was created in a paper published in 2008. It involves the techniques of blockchain and miners working with the computers together in the internet. I give a brief idea of blockchain here. A block refers to the information about transactions. Miners apply the techniques of encryption and digital signature to verify the validity of the current transactions in the internet. Then place them in a block. The verified blocks are linked up in a chain according to the time of the blocks created. To form a new block, miners use the function SHA-256 to convert all information in the last block of the chain and add on the basic information of the current block, plus the transaction records of the current block. All the information of the new block is converted by SHA-256 into a string of 0 and 1. There are many miners working in different places of the world for the new blocks. To avoid too many blocks of current transactions uploading to the internet at the same time, giving difficulty of lining up the blocks, a proof of work is required to fulfill before uploading. The proof of work is to find a random number to paste at the end of the string formed, and we got this as a new string. Apply the function SHA-256 to the new string. If the result contains 72 zeros in the front part of the SHA value, then the work is done. As SHA values are assigned randomly, the probability that a random number is done successfully equals to 1/2 to the power 72. On average, it takes 10 minutes to find such a random number. The first block uploaded to the internet and verified by miners of the network to make sure all information and requirements done correctly will be the successful new block, and it will be placed at the end of the chain. There are many miners around the world working for finding the random number and uploading a new block. The successful miner will be given some bitcoins as reward. In 2017, the reward of forming a new block is 12.5 bitcoins, plus a transaction fee, 2 coins on average. 14.5 bitcoins refer to lots of money and attract many people around the world working with the computers as miners for the blockchain. For every 210,000 blocks created, the number of coins rewarded for mining or mined is reduced by half. At the beginning, for each block from the first to 210,000 blocks created, 50 coins are mined. Then, for each block in the next group of 210,000 blocks, 25 coins are mined. Similarly, each block in the next group, 12.5 coins are mined. Finally, no coin will be mined from the 693,000 and the first block onwards. Miner can earn transaction fee only for the new block. The coins given to the miners are not new coins from that time onwards. In this way, the total number of bitcoins mined is a fixed number. What is this number? Suppose the first bitcoin was mined at the beginning of January 2009. Assume that it takes 10 minutes to create each new block. How many bitcoins will be mined by the end of 2022? I leave both questions to you as an exercise. Due to the limited time, I can only give a very brief idea of cryptography and Bitcoin. If you want to know more about cryptography, you may find a book for a proper learning. Here, I recommend a book for your reference. The Code Book, written by Singh. The subtitle of the book is The Science of Secrecy from Ancient Egypt to Quantum Cryptography. The book covers some illustrative highlights in the history of cryptography since ancient times. Why and how cryptography took place in the history and modern commercial business. The ideas and techniques of cryptography are well illustrated in different periods of time. It is a nice book for beginners to have a good picture of cryptography. For the idea of Bitcoin and blockchain, the following videos give a clear picture. 比特幣的原理 The video is in 普通話 with subtitle.